Welcome to Earth, Analyst, the place where curiosity finds calm and knowledge flows gently like the rhythm of the universe. Tonight, we take a slow and soothing journey back in time, billions of years ago, to witness the birth of our home planet Earth. From swirling cosmic dust and fiery collisions, to the cooling of oceans and the rise of continents, this story unfolds quietly, designed to help you relax, drift off, and dream while learning about the mysteries of creation. So, close your eyes, settle in, and let's begin the story of how the Earth was formed. There was a time when vast oceans swallowed whole continents, a time when the skies belonged to insects as large as dragons. Volcanoes rose and reshaped the land in moments. This was the face of prehistoric Earth. About 566 million years ago, our planet was a restless canvas of change. Strange creatures thrived long before the first dinosaur walked the land. Trilobites crawled across the seafloor. Supercontinents like Gondwana and Pangaea formed, broke apart, and drifted again. Fern forests grew even at the poles, while deserts replaced ancient seas. Each era brought new life, some beautiful, some bizarre, many short-lived. The Cambrian period marked the beginning of something extraordinary. It was the first great chapter of the Paleozoic era, a turning point when life began to grow more complex and visible. This age lasted for nearly 52 million years. It began around 538 million years ago and ended 486 million years ago, giving way to the Ordovician period. At that time, Earth looked very different. Most land was in the southern half of the globe. All of it was surrounded by a single vast ocean called Panthalassa. Gondwana was coming together, its pieces colliding and fusing into a supercontinent. This slow dance of tectonic plates built new mountains and sparked volcanic activity. It also warmed the planet. Meanwhile, a landmass called Laurentia sat near the equator, divided from Gondwana by the widening Iapetus Ocean. But the most remarkable story of the Cambrian was life itself. Before this period, most creatures were tiny and simple. Fossils of such organisms are extremely rare. But during the Cambrian, something dramatic unfolded. Life exploded into diversity. This event, known as the Cambrian explosion, gave rise to the first ancestors of nearly all major animal groups alive today. Special fossil sites from this time preserve not only hard shells, but also the soft tissues of creatures. These rare finds give us detailed snapshots of early life in astonishing clarity. The name Cambrian comes from Cambria, the Latin word for Wales. In 1835, the geologist Adam Sedgwick first named and described this period after studying rocks in that region. At first, Sedgwick divided it into Lower, Middle, and Upper Cambrian. He worked with another geologist, Roderick Murchison, but disagreements soon grew. Their debates over boundaries lasted for decades, even after both men had passed. In 1879, Charles Lapworth offered a solution. He proposed a new period, the Ordovician, to settle the dispute. Finally, in 1960, the Cambrian was formally accepted in its modern definition. Today, geologists divide the Cambrian into 4 series and 10 stages. To define the beginning, they use a precise marker in rocks called a global boundary stratotype section and point, or GSSP. In 1994, scientists chose a site in Newfoundland, Canada. The appearance of a tiny burrow, made by a creature called Treptichnus pedum, marked the official start of the Cambrian. It was the trace of more complex behavior, the sign of a world about to change forever. Early estimates once placed the start of the Cambrian at 570 million years ago. With better dating methods, we now know it began around 538.8 million years ago. The margin of error is only about 500,000 years. This age comes from volcanic ash layers in Oman. These rocks also show a drop in carbon-13 and the disappearance of older life forms. Still, some scientists argue this is not the true boundary. They prefer slightly older estimates, between 544 and 542 million years ago in Russia. Paleontologists often begin the Cambrian with the Tomotian stage. This stage is marked by the first skeletal fossils and the rise of early reefs. To understand the Cambrian more clearly, scientists divide it into 4 parts. The first is the Terrenvian series, from 538.8 to 521 million years ago. It has no trilobite fossils. Instead, it contains small shells and early burrows. The name was made official in 2007. Next is Cambrian Series 2, from 521 to 509 million years ago. It includes stages 3 and 4. During this time, animal diversity increased rapidly. Trilobites and archaeocyathid reef builders flourished. Comparing rocks worldwide is difficult, since fossils vary by region. After this came the Myelingian series, lasting from 509 to 497 million years ago. It includes the Woollywan, Drumian, and Gujangian stages. Approved in 2018, it was named after the Miaoling Mountains in China. This era began with the trilobite, or Octocephalus indicus. At its boundary, many trilobites went extinct. This is considered the first mass extinction of trilobites. The final part of the Cambrian is the Pharongian series. From 497 to 486.9 million years ago, the name was approved in 2003, replacing the older Upper Cambrian. It begins with the trilobite Glyptognostus reticulatus. The series includes the Pabian, Jiangshanian, and a final unnamed stage. The boundary between the Cambrian and the Ordovician is set at Greenpoint in Newfoundland, Canada. It is dated at 486.9 million years ago. This point is marked by the appearance of a tiny tooth-like fossil called Eopatognathus fluctivigus. In areas where it is missing, other markers, like plankton, fossils, or trilobites, are used instead. During the Cambrian, Earth was struck by several large meteorites. Around 535 million years ago, an impact created the Newgrind crater in Estonia, about 20 kilometers wide. Another, the Gardanos crater in Norway, formed around 500 million years ago in a shallow sea. It is about 5 kilometers across. The climate of the Cambrian was mostly warm and humid. Evidence comes from the rocks left behind. These include carbonate platforms in tropical seas, reefs built by sponge-like organisms, and deposits of bauxite that form in warm, wet conditions. Evaporites and calcretes also appear, showing that some regions were dry and arid. Altogether, these signs tell us the Earth was in a greenhouse climate. There were no large ice sheets. Temperatures stayed high across most of the planet toward the end of the Cambrian. Trilobite fossils suggest that temperature differences between the poles and the equator were small. Even the polar regions were not very cold. Some scientists claim to see evidence of glaciers in Avalonia, a landmass near the South Pole at the time. But there is still debate over whether these icy rocks belong to the Cambrian or to the earlier Neoproterozoic period. Measuring Earth's temperature during the Cambrian is not simple. Different methods give different results. Some early estimates suggested global averages above 40 degrees Celsius, but more reliable models point to gentler numbers, around 20 to 22 degrees at the start of the Cambrian, later rising to about 23 to 25 degrees for much of the period. This long warmth was linked to high levels of carbon dioxide. Gondwana, the great supercontinent, was coming together. As the plates moved, new boundaries formed. Volcanoes erupted along these edges. They released carbon dioxide into the air. A major volcanic event, the Kalkaringi Large Igneous Province, erupted during stage 4 of the Cambrian. It spilled into the early These eruptions released carbon dioxide, methane, and sulfur dioxide. The gases heated the planet. They raised sea surface temperatures to new highs, but there is still debate about how hot the oceans really became. Scientists study oxygen isotopes in ancient rocks to find out. Some estimates place tropical seas between 28 and 32 degrees. Others suggest 29 to 38 degrees. Today, tropical oceans average about 26 degrees. By comparison, the Cambrian seas were warmer. Even as heat rose, oxygen in the air stayed low. Levels ranged from only 3 to 14%. Far below today's 21%. With less oxygen in the atmosphere, less dissolved into the oceans. The deeper waters often became anoxic, almost completely without oxygen. These conditions strongly shaped early marine life. As new creatures burrowed into sediments, they stirred up the mud. This process, called bioturbation, exposed oxygen-poor layers to oxygen-rich waters above. It reduced the burial of organic carbon and sulfur. Over time, this slowed the buildup of oxygen in the air and seas. Oxygen shortages spread deeper across the oceans. At the same time, weathering on land sent nutrients rushing into the seas. Phytoplankton, tiny photosynthetic organisms, bloomed in great numbers. Their growth fueled the rise of more complex animals. But when blooms grew too quickly, they created eutrophication. Excess organic matter sank, decomposed, and consumed oxygen. Waters turned depleted once more. Cycles of warmth, oxygen shortage, and renewal shaped the course of evolution. They guided the first steps of animal life on Earth. When oxygen levels rose, life flourished. More oxygen allowed bigger body sizes, more energy, and more complex ecosystems. The habitable seafloor expanded. But when oxygen fell, many creatures struggled. Drops came from sea level changes, shifting currents, or deep oxygen waters rising to the surface. These events triggered extinctions. Sometimes they struck only one region. Other times they spread across the globe. The Cambrian was an age of dramatic ups and downs. Oxygen-rich times brought bursts of biodiversity. Oxygen-poor times forced extinctions. These swings drove innovation. Species vanished, but others adapted in remarkable ways. On land, plant life was nearly absent. The seas held large algae, such as Fucsianospira, Cynosolindra and Marpolia, but no calcareous algae have been found from this time. Land plants, known as embryophytes, left no fossils from the Cambrian. Instead, microbes thrived. Biofilms and microbial mats spread across tidal flats and beaches as early as 500 million years ago. These communities worked like modern soil crusts. They stabilized the ground and helped form the first soils. Some studies suggest land plants may have begun in the Middle or Late Cambrian, but this idea is still debated. The large-scale removal of carbon dioxide by plants did not begin until the arthropods - relatives of insects and spiders may also have begun moving onto land. Genetic evidence hints at this, but the oldest clear fossils appear later in the Ordovician. Their Cambrian origin remains uncertain. The Cambrian explosion was a turning point. It began around 541 million years ago. Life became more diverse, more complex, and more visible. Multicellular creatures. Most lived in the oceans. For many years, scientists thought trilobites were the dominant animals. These armored creatures left behind countless fossils. But newer research shows a fuller story. Trilobites were important, yet they were only one part of a much larger group. This group includes insects, crabs, and spiders. In Cambrian seas, soft-bodied arthropods were far more common, but their delicate bodies rarely fossilized. Trilobites, with shells made of calcium carbonate, preserved easily. This made them seem more abundant than they truly were. The Cambrian explosion marked a new chapter. Life expanded quickly. The number and types of species multiplied, but not all survived. Some vanished in extinction. Others adapted, paving the way for the world to come. The Ediacaran, soft-bodied organisms that lived before the Cambrian suffered a mass extinction. Around the same time, new animal behaviors appeared. One of the most important was burrowing into the seafloor. These burrowing creatures changed the ocean floor in ways that could not be undone. Before this, the seabed was mostly covered by thick microbial mats. They were like slimy blankets of microorganisms. But as animals dug through the sediments, they disrupted these mats. Over time, they destroyed many of them in a process called bioturbation. This forced the creatures that relied on the mats either to adapt or die out. Those that could adjust began to take advantage of the new habitats forming in the disturbed seabed. During this same period, animals with hard mineralized body parts became more common. Shells and skeletons began to appear. These included representatives from most of the major groups of animals that we still recognize today. One example is the bryozoans, tiny colonial organisms that were once thought to have appeared later in the Ordovician period. But most of these early forms were only primitive ancestors of today's species. They did not fully represent the diversity of soft-bodied life. Many other creatures may have been far more abundant, but rarely preserved. Even though the early Cambrian period was a time of extraordinary growth, earning it the name Cambrian explosion, this boom did not last forever. Around 515 million years ago, things began to change. The number of species going extinct started to outpace the number of new ones appearing. About 5 million years later, the total number of different genera fell from around 600 to about 450. The rate of new species formation dropped to only a fraction of what it had been earlier. Perhaps just 1/5 or 1/3 by 500 million years ago. Oxygen levels in the oceans declined sharply. This caused hypoxia, a situation where oxygen was too scarce for most animals to survive. At the same time, levels of hydrogen sulfide, a toxic gas, began to rise. This dangerous combination led to another extinction event. The second half of the Cambrian was much quieter. It was less biologically rich than the first. Several quick waves of extinction occurred. Reef-building sponges, called archaeocyaths, eventually died out. They had once replaced the older reforming organisms known as stromatolites. After their disappearance, stromatolites made a brief comeback, but overall biodiversity stayed low until the Great Ordovician biodiversification event, which brought another explosion of life later on. Life in the Cambrian oceans was not easy. Oxygen levels were low and unpredictable. When deep, oxygen-poor waters rose into shallower areas, a process called upwelling, whole communities could vanish. Yet these stresses pushed evolution forward. They encouraged new adaptations and set the stage for greater biodiversity in the future. Some Cambrian animals even began to explore the land. Fossils of their movements, known as trace fossils, have been found. Two types are called productnites and climactic. Scientists believe some productnites' tracks were made by an extinct arthropod known as a As for climacticnites, the actual animal has not been discovered, but the tracks and resting marks suggest a large, soft-bodied creature, possibly something like a giant slug or an early mollusk compared to later ages. The variety of animals in the Cambrian was still limited, but the patterns of survival, adaptation, and extinction shaped the path of life for the ages to come. Creatures that floated freely in the water were rare. Most animals lived on or just above the seafloor. Animals with mineralized shells or skeletons were also less common than they would later become. One reason for this was the chemistry of the oceans. The water was not ideal for forming or preserving hard body parts. Despite these limits, the Cambrian gave us some of the most remarkable fossil discoveries ever found. Many fossils from this time preserved not just bones or shells, but also soft tissues. Skin, gills, and digestive systems are sometimes visible, things that almost never survive in the fossil record. These rare fossil sites are called Lagerstätten. They offer an extraordinary window into ancient life. Some of the most famous include Sirius Passet in Greenland, the Sinsk biota in Russia, the Maotianchan shales in China, the Emu Bay shale in Australia, and the Burgess shale in Canada. Each site captures delicate details of life more than 500 million years ago. The Ordovician period marked the next great chapter in Earth's story. It was the second period of the Paleozoic era. It was also the second of 12 major divisions that make up the Phanerozoic eon, the long span of time that includes most of Earth's complex life. The Ordovician lasted about 41.6 million years. It began around 486 million years ago, right after the Cambrian ended. It came to a close about 443 million years ago. When the Silurian period began, the name Ordovician comes from the Ordivices, a Celtic tribe that once lived in what is now Wales. The period was officially named in 1879 by a British geologist named Charles Lapworth. At the time, two other geologists disagreed about certain rocks in northern Wales. Adam Sedgwick believed they belonged to the Cambrian. Roderick Murchison argued they were from the Silurian, but Lapworth noticed something important. The fossils in those rocks were different from both the Cambrian and the Silurian. He proposed a brand new period, the Ordovician, to solve the dispute. It was not until 1960, more than 40 years after Lapworth's death, that the International Geological Congress formally accepted the Ordovician as an official period. During the Ordovician, life in the oceans did more than survive. It flourished. The great expansion of biodiversity that began in the Cambrian continued. The seas were filled with invertebrates, especially mollusks and arthropods. Arthropods were particularly important. Some of them may have even started to move onto land, although they would not become fully established there until the Devonian, which came later. This period also saw the appearance of the very first land plants. They were small and simple, but they signaled greater changes to come. The world was preparing for an even more complex future. One of the most exciting events was the Great Ordovician biodiversification event. During this time, the variety of life forms expanded dramatically. It was also in the Ordovician that fish, the first true vertebrates, began to evolve. Evidence even suggests that fish with jaws may have appeared near the end of this period. Something unusual also happened in the sky. During the Ordovician, Earth was bombarded by about 100 times more meteorites each year than we see today. This strange event is known as the Ordovician meteor event. Some scientists think it might have been caused by a temporary ring system that briefly formed around the Earth. The climate of the early Ordovician was extremely hot. The planet was in a greenhouse state, with sea surface temperatures as high as those seen in the later Eocene climatic optimum. At the beginning of the Ordovician, the atmosphere contained very high levels of carbon dioxide, but this did not last. By the later part of the early Ordovician, the planet began to cool. It entered a more temperate phase during the middle of the period. Eventually, the Earth shifted into a long icy phase called the Early Paleozoic Ice Age. This cold period may have begun as early as the Floyan Age, or perhaps slightly later during the Darwinian or Sandbian stages. During the Dipingan and Sandbian, heavy rainfall occurred, as shown by metal traces preserved in rocks from the region now called Baltoscandia. In the early Cation stage, temperatures rose again for a short time. This is called the Boda event. It led to the growth of reef-like structures and a rapid spread of marine life across what is now Europe. Another phase of heavy rain also occurred in the early Cation, but after that, Earth cooled again, eventually leading to a major glacial period. This is known as the Hernontian glaciation, which took place at the very end of the Ordovician. During this time, sea levels were higher than at any other point in the Paleozoic era. Most of the continents were flat and low-lying, so shallow seas covered vast areas of land. These warm, shallow waters supported many marine creatures, especially those that built hard shells or skeletons out of calcium carbonate in the early Ordovician. Sea levels rose steadily and stayed high through the middle of the period. There were some local drops in sea level, but the overall trend continued upward into the early late Ordovician. Then, As Earth grew colder in the millions of years leading up to the Hernanchean glaciation, sea levels began to fall. During the glacial period, sea levels rose and fell many times. The exact pattern is still debated. Some scientists think these changes began even before the Hernanchean glaciation officially started. But clear evidence of glaciers only appears at the very end of the period. Proof now shows that glaciers formed across what are today Africa and South America. At that time, both of these lands were near the South Pole together. They built the icy caps of the ancient glacial age, much like North America and Europe. The great southern continent, Gondwana, was mostly covered by shallow seas during the Ordovician. These warm, sunlit waters created the perfect environment for life. They gave space for creatures that built shells, reefs, and skeletons to thrive. Across the north stretched the vast Panthalassic Ocean, covering much of the hemisphere. Several other ancient seas and oceans also existed. Among them were Prototethys, Paleotethys, the Iapetus Ocean, which disappeared by the end of the period, the Rheic Ocean, and a few smaller basins. For most of the late Ordovician, ocean life flourished. Many different marine animals thrived, and ecosystems grew increasingly complex. But as the period drew to its close, something dramatic, a series of extinction events, struck the seas. Tiny, tooth-like creatures called conodonts and floating organisms known as graptolites were hit especially hard. Two entire groups of trilobites, the Agnostida and the Trinoclida, vanished completely. Another group, the Asaphida, declined to just a few remaining forms. Other animals suffered greatly as well. Brachiopods, which looked like clams, and bryozoans, which built coral-like colonies, both declined. Echinoderms, the relatives of starfish and sea urchins, also fell in number. A squid-like creature called the Endosauroid cephalopod was almost entirely wiped out, surviving only as rare forms in the next period. The Silurian scientists believe this mass die-off was driven by a sudden ice age at the end of the Ordovician. The cooling may have been triggered by the spread of the first land plants, which pulled large amounts of carbon dioxide from the atmosphere and changed the climate. The final part of the Ordovician became one of the coldest intervals of the last 600 million years. Even so, the Ordovician was a time of great growth. It produced a wide range of new marine life that shaped the rest of the Paleozoic era. The oceans filled with animals that filtered tiny particles from the water for food. They formed simple but connected food chains, building dense and thriving communities. Life in the Ordovician was far richer and more complex than in the earlier Cambrian. The pattern of ocean life that took hold then has, in many ways, continued all the way to the present. One of the most remarkable events of this time was the Great Ordovician Biodiversification Event. It may not be as well known as the Cambrian explosion, but it was equally important. During this event, the number of marine animal genera grew by 4 times. This represented about 12% of all known marine life in the entire Phanerozoic eon. Many animals also became smaller compared to their Cambrian ancestors. Filter-feeding organisms, in particular, became more widespread than ever before. By this point, the old Cambrian forms were fading away. Inarticulate brachiopods, archaeocyathids, early echinoderms, and primitive trilobites all declined. In their place rose new groups, Articulate brachiopods with hinged shells became dominant. Crinoids, or sea lilies, spread widely. And cephalopods, relatives of modern squids and octopuses, emerged in many forms. Articulate brachiopods, especially, began to take control of the ocean shelves, pushing trilobites into decline across many regions. These changes reflected a big increase in animals that made hard, shell-like coverings from carbonate minerals. The layout of the continents during the Ordovician also had a big effect on what kinds of animals evolved. Different areas developed their own unique types of invertebrate life. For example, the continents of Laurentia and Beltica, which were near the tropics and surrounded by shallow, warm seas, had their own kinds of trilobites, different from those found in Gondwana itself had separate animal groups in its warm and cooler regions. Parts of Central Asia, like the Tian Shan area, were closely related to Gondwana in terms of life forms. The Alborz region of what is now Iran also shared connections with South China. Southeast Asia's sea life had strong ties to Gondwana as well. North China shared similarities with both Laurentia and parts of South America that were part of Gondwana. There was even a unique group of animals living in what scientists call the Celtic province. However, some animals, like the tropical articulate brachiopods, lived all over the world and weren't limited to just one region. As the Middle Order began, the spread of marine animals across the world increased. As a result, fauna became less provincial, meaning they were more widely shared between regions, especially as oceans like the Apatitis Ocean grew smaller. Still, differences in marine life between areas continued up until the end of the Ordovician. Trilobites, those armored sea creatures with jointed legs and many eyes, were especially abundant and diverse. They evolved rapidly during the Ordovician and developed all sorts of strange features. Some grew long spines and bumps to protect themselves from predators like early sea scorpions, euripids, and predatory cephalopods. One trilobite called a gleeper even learned how to swim. Others developed wide snouts for digging through ocean mud. A group known as the trinlades had strange flat-pitted borders around their head shields. Some trilobites, like a surface kowski, grew long stalks on their eyes to help them see predators from a distance, while others lost their eyes completely. By the end of the order, early arachnids, relatives of spiders and scorpions, may have started making their way onto land. Although single coral animals had existed since at least the Cambrian, large reef-building corals appeared during the early Ordovician, along with the first known soft-bodied octocorals. This increase in coral reefs also meant there were more animals that use calcium to build shells and skeletons. Brachiopods became incredibly diverse, adapting to nearly every marine environment, from shallow shores to deeper waters. Even after the great biodiversification, they continued to evolve quickly. Mollusks, which had first appeared either during the Cambrian or possibly even earlier in the Ediacaran, also became more common and came in many shapes and sizes. These included clams, bavs, snails, gastropods, and straight-shelled cephalopods called nautiloids, which spread from shallow tropical seas to nearly every part of the ocean. Grappalites, tiny colonial animals that floated in the ocean, thrived throughout this time. A particular group called Nemagus gracilis became widespread during a period of especially high sea levels in the sand. New types of crinoids and cystoids, ancient toinoderms, also appeared. Although scientists used to believe that the first real fish appeared in the order of vision, fossil discoveries from China now show that jawless fish, ostracerms, likely already existed in the early Cambrian. The very first jawed fish, gnathosomes, may have started to appear during the late Ordovician. Tiny flask-shaped microwassels, known as Chitina-zoans, which first showed up in the late One Age, went through a huge boom in the early part of the Ordovician. The Tremodosian quickly spreading across the globe. Several animals during this time also formed partnerships called symbiosis, where different species live closely together for mutual benefit. At the beginning of the Ordovician, trilobites were joined by many new kinds of sea creatures. These included tabulate corals, many new types of brachiopods like straphominids and rhinellids, branching bryozoans, floating grappolites, conodonts, and all sorts of mollusks, necodyms. This group even included the first brittle stars, ophids, and true starfish. Arthropods, the group that includes insects and crustaceans, continued to be abundant. Older trilobite orders from the Cambrian stuck around, and a new one called Phacopoda emerged. The earliest evidence of land plants also appeared during the Ordovician, marking the beginning of a major change in Earth's ecosystems. In the middle of the order, ocean communities began to change. Trilobites became less dominant, and ecosystems became more balanced and diverse. Brachiopods, bryozoans, mollusks, and anoderms flourished. Corals became more varied, with tabulate corals spreading and the first horn-shaped rugose corals appearing. Planktonic graptolites continued to diversify, and a new group called the diploina emerged. One of the earliest known armored jawless fish, called Arundospis, lived during this time. The Middle Order also saw a big increase in animals that burrowed into hard materials, like shells and rocks. This period is called the Order of Vision, Bioerosion, Revolution. Scientists know this because of the sudden appearance of many boring trace fossils with names like trypanites, Peleosabella, Petros, and Osprionite. Bioerosion became an important force, especially in thick-shelled animals like corals, bryozoans, and brachiopods, as well as in the vast hard seabeds made of carbonate rock that were common during this time. During the later part of the Cambrian period, and even more so in the Ordovician period that followed, green algae were already quite common. These green algae are thought to be the ancestors of the first land plants. Sometime during the middle to late part of the Ordovician, more than 460 million years ago, tiny soft-bodied plants that looked like modern-day liverworts began to appear on land. These early plants did not have vascular systems, which means they couldn't move water or nutrients through their bodies the way most modern plants do. Fossilized spores found in order rocks are similar to those of bryophates, a group that includes mosses and liverworts today. Alongside the first land plants, some of the earliest fungi were also starting to thrive. Among them were special fungi known as abuscular microaceae, which belonged to a group called the glomamorels. These fungi formed an important partnership with the early plants by attaching to their roots. In exchange for sugar from the plants, the fungi helped gather minerals from the soil and pass them to the plant cells. This kind of teamwork, called mycorrhizal symbiosis, was essential for helping plants survive on land. Fossils of these fungi, including their thread-like hay and tiny spores, have been found in order rocks from what is now the U.S. state of Wisconsin. These fossils are about 460 million years old, from a time when land was mostly empty, except for simple moss-like plants and these helpful fungi. Meanwhile, in the oceans, strange structures called stromatolites formed by layers of microorganisms, mostly bacteria, were still around, although they were far less widespread than they had been during the Proterozoic eon, billions of years earlier. By the Ordovician, stromatolites only appeared in specific, isolated places. The Ordovician period ended in dramatic fashion. A series of extinction events swept across the oceans and wiped out a huge number of living things. Altogether, these disasters make up the second largest mass extinction in Earth's entire history. Only the much later Permian-Triassic extinction was worse. These devastating extinctions happened between 447 million and 444 million years ago, right at the boundary between the order of vision and the next period, the Silurian. At that time, all complex life still lived in the sea. Nearly half, about 49%, of all animal genera wiped out forever. Groups like brachiopods and bryozoans were hit especially hard. Many kinds of trilobites, conodonts, and graptolites also vanished. Most scientists believe that these extinctions were caused by a sudden shift to colder global conditions. The warm, stable greenhouse world of the Ordovician gave way to an ice age, starting in the late Catian stage and peaking during the Hernand age. Glaciers began to grow, and global temperatures dropped. Oxygen isotope data from fossil brachiopods suggest this ice age may have lasted for only about 500,000 to 1.5 million years. However, some studies suggest that cooler conditions didn't truly fade until well into the Silurian period. One of the key reasons the Earth cooled was a dramatic drop in atmospheric carbon dioxide. During the Ordovician, carbon dioxide levels may have fallen from about 7,000 parts per million to just 4,400 parts per million. One possible cause was increased volcanic activity, which laid down fresh silicate rocks. As these rocks slowly eroded, they absorbed carbon dioxide from the air. Another explanation is that newly evolved mosses, liverworts, and lichens on land increased chemical weathering, also pulling carbon dioxide out of the atmosphere. With less carbon dioxide, the greenhouse effect weakened, and the Earth began to cool, especially in the shallow seas where most marine life lived. There's also a fascinating hypothesis that Earth may have had a ring system during the order of Vitium. If such a ring existed, it could have blocked some sunlight, contributing to the cooling. In addition, a major meteor event during this time may have played a role in climate change. As the southern supercontinent Gondwana drifted over the South Pole, thick ice sheets formed on top of it. We know this from glacial features found in upper Ordovician rocks in North Africa and in parts of what is now Northeast and South America, areas that were near the South Pole during that time. As the glaciers expanded, sea levels dropped dramatically. Shallow inland seas that once teemed with life drained away, destroying many marine habitats. When the seas briefly returned, they brought with them smaller, less diverse communities of life. Then, with another wave of glaciation, the seas withdrew again, leading to further extinctions. This back and forth pattern deeply affected life in these shallow marine environments. Species that lived in only one particular inland sea were especially vulnerable. The first wave of extinction mostly affected tropical species, while the second wave dealt a harder blow to those adapted to cooler waters. Despite the devastation, some life forms managed to adapt to the new environment during the coldest period. Ocean waters became more oxygenic at deeper levels, allowing new bottom-dwelling organisms known as the Hinont fauna to move in. These creatures spread widely and lived in many different parts of the world. Eventually, the Ice Age came to an end. As the glaciers melted, sea levels rose again and stayed high. With the flooding of the continental shelves came a burst of new life. Many of the surviving groups began to diversify, filling the gaps left by extinct species. Interestingly, some species that disappeared during the extinction later reappeared in the Silurian period. Scientists call these Lazarus taxa since they seem to have come back from the dead. It's likely that these organisms survived in small, hidden environments called refugia, where they waited out the worst of the changes. One alternate theory suggests that a powerful gamma ray burst from space may have hit Earth for just 10 seconds. This could have stripped away the ozone layer and exposed surface life to deadly ultraviolet radiation, leading to mass death and possibly triggering a cooling trend. More recent studies suggest that the entire late Ordovician extinction might not have been two separate events, but rather one long and drawn-out crisis. This event likely lasted several hundred, 0 years, and involved sudden shifts in sea level and sediment patterns that caused waves of extinction. The Curon period was a remarkable chapter in Earth's history. It lasted for about 23.5 million years, beginning at the end of the Eruption period, around 443 million years ago, and ending at the start of the Devonian period, about 420 million years ago. This period was the third out of 6 major periods in the Paleozoic era, and the third of 12 periods in what scientists call the Phaneroic Eon, the time when visible, complex life flourished on Earth. Even though geologists have clearly marked the layers of rock that signal the beginning and end of the exact timing is still uncertain by a few million years. The Silurian began right after a devastating global event, one of the biggest mass extinctions in Earth's oceans. During this crisis, around 60% of marine species vanished. It marked a dramatic turning point and a new beginning for life on our planet. One of the most exciting things about the Silurian was that life began to colonize the land in earnest. This major leap is often called the Curon-Devonian terrestrial revolution. Before this time, most life was underwater, but now plants and animals were starting to adapt to life on dry ground. Early land plants that had no roots or vascular systems began to evolve into vascular plants, which could transport water and nutrients internally and grow taller. Alongside them, new types of fungi, especially Dicarian fungi and glomeromycotin fungi, spread and diversified, helping plants form root systems and survive in rocky, harsh environments. At the same time, 3 important groups of arthropods, myriads like millipedes, arachnids like spiders, and hexapods, insects and their relatives, became fully adapted to life on land. This was the first wave of animals to permanently leave the ocean behind. The Silurian also witnessed an explosion in the variety of jawed fish. New groups such as pletums, armored fish, anthodians, which would give rise to modern sharks, and rays and ostichans, bony fish, made their appearance. The bony fish later split into two types: lobby-finned fish, which would eventually lead to amphibians and humans, and ray-finned fish, which dominate the seas today. However, as these jawed fish thrived, the older jawless fish, like ostracoderms and conodonts, began to decline. The balance of power in the ocean was shifting. The Curon period was first named and described in the early 1830s by a Scottish geologist named Roderick Murchison. He studied fossoric rock layers in southern Wales and decided to name the period after the Salar, an ancient Celtic tribe that once lived in the region. This naming was inspired by his friend and fellow geologist Adam Sedgwick, who had earlier named the Cambrian period after another Latin name for Wales. However, Murchison's identification of Silurian rocks in certain areas overlapped with the rocks that Sedgwick had assigned to the Cambrian. This led to a fierce scientific rivalry that ended their friendship. Eventually, an English geologist named Charles Lapworth solved the conflict by creating a new period between the Cambrian and Silurian, which he called the Eruptions. Elsewhere, some scientists used a different name for the Gotlandian after rocks on the island of Gotland. See the French geologist Joachim Barrandi expanding on Murchison's work divided Silurian rocks in Bohemia in what is now the Czech Republic into 8 stages, though. Later studies revealed that some of these actually belong to the Dionian period. Still, his work made Bohemia one of the most important regions for studying early Silurian fossils. During the Silurian, the ancient supercontinent Gondwana covered the equator and stretched across much of the southern hemisphere. Meanwhile, a huge ocean spread across the northern half of the globe. Because sea levels were very high and most land was low and flat, many small islands formed, creating all kinds of different environments for life to thrive. Gondwana continued to drift slowly southward, but the ice caps from the previous period's glaciation began to melt. This led to rising sea levels. In many places, Silurian rock layers lie directly above eroded or division rocks, which tells geologists that the seas flooded back over the land. At the same time, the continents, Avalonia, Baltica, and Laurentia, were drifting toward the equator and eventually collided. This was the beginning of a new supercontinent called Europe. When Proto-Europe smashed into North America, it squeezed and folded layers of ancient sediments that had built up for millions of years. This powerful geological event is known as the Caledonian Orogeny, a mountain-building phase that affected a huge area from present-day New York State, across Greenland through Europe, and all the way to Norway. As the Curon came to a close, sea levels dropped again. This drop left behind salty basins, evaporate deposits stretching from Michigan to West Virginia. The freshly formed mountain ranges also began to wear down quickly. One ancient river, the Tees River, carved into older O-division rocks and left behind Silurian sediments in what is now northern Ohio and Indiana. In the northern hemisphere, the massive ocean called Panthalassa dominated the scene. Other seas and oceans included 2 early versions of the Tethys Ocean, the Prototethys and the Paleotethys. as well as the Rik Ocean, the Arpatus Ocean, a narrow sea between Avalunia and the newly formed Ural Ocean. The Silurian period was once thought to have been a time of calm, steady warmth. This was in contrast to the icy extremes of the Orivisian period before it and the intense heat that followed in the Dionian period. But today, scientists know that the Silurian climate was anything but stable. In fact, the planet went through many dramatic climate shifts during this time. We know this because of major changes seen in carbon and oxygen isotopes, chemical clues left behind in rocks from that era. Sea levels also changed greatly during the sea. At the beginning of the period, they rose significantly from their low point during the Hernand glaciation, then slowly dropped again toward the end. However, this wasn't a simple rise and fall. Sea levels went up and down in smaller cycles, too. Scientists have identified 15 distinct high sea level periods when the ocean rose above the edges of the continents. At its highest, the Curon sea level was likely about 140 meters or 459 feet higher than its lowest point. During the Curon, Earth entered a warm greenhouse phase. The atmosphere was full of carbon dioxide, about 4,500 parts per million, much higher than today's levels. Warm, shallow seas spread out across the tropical regions of the planet. In the early Silurian glaciers that had once reached into the continent shrank and slowly retreated back toward the South Pole, almost vanishing by the middle of the period. The climate of this time was also marked by fierce and frequent storms. We can tell this from thick layers of koina rocks made up of broken shells that were formed by storm-driven waves pounding the seafloor. The Silurian climate and carbon cycle were surprisingly unstable, showing more frequent shifts than in any other geological period. Scientists have named several of these dramatic events, such as the Erevakan event, the Mula event, and the Lau event. Each of these was marked by a small extinction, sudden sea level changes, and sharp changes in carbon isotope levels. The creatures that lived freely in open waters, like plankton, were hit especially hard. Brachiopods, corals, and trilobites also suffered. These extinction events often unfolded quickly in rapid bursts. Some researchers believe these fluctuations were due to repeated glaciation, but because there are few glacial deposits, like tylites, from the middle to late Silurian, this idea is still debated. Paleontologists see the Silurian as a time when life was still recovering from the late Eruption mass extinction, a massive event that had disrupted the steady rise of biodiversity that began in the Cambrian and carried through most of the Ordovician. But the Silurian wasn't just about recovery. It was also a period of exciting new beginnings. For the first time in Earth's history, large fossils of land-based life appeared. These included small, moss-like plants growing along lakes and streams, forming the first primitive forests. There were also large, fungal-like organisms known as netopites, which lived in networks and likely had a close relationships with underground fungi. This was the dawn of the Curian-Dionian terrestrial revolution, when life slowly began to conquer the land. However, these early land organisms didn't yet have a major effect on the planet. That would come later in the Devonian. In the second half of the Curon, a truly important event took place: the appearance of the first vascular plants. These were land plants that had internal systems for carrying water and nutrients. a major evolutionary leap. The earliest known vascular plant was Cussonia, a tiny plant that grew along streams and rivers. Although it was found mostly in marine deposits, it likely lived close to the water's edge. Another plant, Baragwania, which had needle-like leaves and branching stems, also appeared around the same time, about 420 million years ago, during the Lelo epoch. Fossils of Baragwania have been found in Australia, Canada, and China, and they show a surprisingly advanced structure for such an early plant. Another early land organism, possibly a plant, was a Hostomela hetha known from compression fossils from the early Silurian, specifically the land ovary epoch. Its chemistry is more like that of vascular plants than algae, which hints that it too may have been a land dweller. The Curian was also home to the earliest known terrestrial animals. Fossils from around 425 million years ago on the island of Carrera show millipedes like Campicaris, Obanus, and Acid. Other fossils from the Lelo epoch, around 420 million years ago, show millipedes, centipedes, and spider-like creatures called trigonotids. These animals suggest that simple food chains were already forming on land, with predators feeding on smaller creatures. In 1990, a team led by Andrew Graham proposed that there were likely many more land creatures, such as tiny grazers and decomposers, that we haven't discovered yet. Fossils from the Cowie Formation, including Cowie desmos and Pneumodesmus, were once thought to be from the Middle Curon, around 428 to 430 million years ago, but later studies suggest these rocks might actually be from the early Devonian. Even so, Pneumodesmus remains hugely important because it shows the earliest known circles, openings for breathing air in a land animal. Underwater, life was booming again. Life was booming again. The first bony fish, known as ostics, appeared during the sea. One group, the Anthodians, were covered in small bony scales. Fish became more diverse and, for the first time, developed jaws that could move, evolved from the front gill supports. The Curon Seas, especially around what is now North America, were home to Europarids, also called sea scorpions, some of which grew several meters long and ruled the shallow waters. Brachiopods, marine animals with hard shells, were still very common. Many had survived the Orevich extinction and adapted to stressful environments. At first, these animals lived in only one region, but later they spread out again. The most successful brachiopods were atripids and pentamerids. Atropids were quick to recover, but pentamides took longer, not bouncing back until the Uronian epoch. Other sea creatures also flourished. Bryozoans, which form colonial structures, often lived only in specific regions and formed symbiotic partnerships with corals and strumatali. Bivalves like clams were common and even began to burrow deeper into the seafloor for the first time. Kittens, marine mollusks with armored plates, reached peak diversity in the middle of the Heteroloids, strange colonial organisms, formed partnerships with certain corals, such as in the Silurian was also the golden age of tentacletoids, a mysterious group of small tube-shaped sea creatures. They thrived, especially in Baltiscandia, and spread widely during the land ovary and Wulak epochs. Even trilobites, the iconic marine aeropods, managed a comeback, though their diversity had dropped after the Orevisian extinction. They still did well during the Quran, especially in the Rhodanian. The Quran also saw new kinds of crinoids or sea lilies. Groups like the Flexibilia which had survived the extinction with little harm, became more common. Monobathrid cameras diversified early, while others, like scythocranids and dendronids, expanded later. An odd group called scyphochronoids appeared suddenly near the very end of the Curian and vanished just as quickly. Symbiosis was everywhere. Corals and strum-autoporoids, reef-building sponges, often had endobiotic symbionts living inside them. Rugose corals in particular were frequently encrusted with ipibionts, such as the heteroids mentioned earlier. And in the Middle Curon, the first photosymbiotic scleractinian corals that lived in partnership with photosynthetic organisms, made their debut. Despite all this richness, Siluran reefs were inconsistent. In some places, reef fossils are abundant, while in others they are nearly absent, leaving puzzling gaps in the fossil record. The Devonian period is one of the most fascinating chapters in Earth's long and dramatic story. It belongs to the Paleozoic era, which is part of the Phanerozoic Eon, the great stretch of time when visible life became common. The Devonian lasted for about 60.3 million years, beginning roughly 419 million years ago at the end of the Curon period and ending around 359 million years ago when the Carboniferous period began. It is the fourth geological period of both the Paleozoic and the Phanerozoic. The name Devonian comes from the county of Devon in southwestern England, where rocks from this ancient time were first carefully examined. During the Devonian, the surface of the Earth underwent extraordinary changes, especially on land. Life that had mostly stayed in the oceans was now beginning to conquer the continents. Plants that could release spores into the air, known as free-sporing vascular plants, like ferns, began spreading far and wide. Over time, they formed lush, dense forests, creating dark green blankets over much of the land. By the middle of the Devonian, many plant species had developed true roots and broad leaves, and near the end of the period, the first plants that produced seeds, called pteridosperm phytes, or seed ferns, appeared. This major transformation of life on land is part of what scientists call the Siluran-Devonian terrestrial revolution. This was not just a quiet spread of mosses and roots. It was a revolution in slow motion, changing the air, the soil, and the entire landscape of Earth. Alongside the rise of plants, the first land-dwelling animals also began to appear. These early creatures were mostly aeropods, invertebrates with jointed legs and hard outer shells. The pioneers included creatures like millipedes, spiders, and early insects, which likely began their journey onto land as early as the Ordovic period. Meanwhile, beneath the waves, the oceans were teeming with life, especially with fishes, which exploded in variety and number. Because of this underwater abundance, the Devonian is often called the Age of Fishes. One group of fish, known as placoderms, had thick, armored plates covering their bodies, and they ruled many ocean habitats. At the same time, a special group of fish called tetrapodomorphs also began to evolve in Devonian freshwater environments. These were the ancestors of all four-limbed animals, including frogs, reptiles, birds, and even humans. Their strong, muscular fins gradually began turning into legs and feet, though they weren't quite ready to walk on land just yet. That leap would come much later in the late Carboniferous period. The Devonian also saw the arrival of the very first ammonites. relatives of modern-day squids and octopuses with spiral shells and tentacles. At the same time, older marine creatures such as trilobites, brachipods, and sprawling coral reefs were still thriving, at least for a while. Sadly, the Dionian story took a dark turn. Around 375 million years ago, a devastating mass extinction event struck the oceans. Many of the great reef systems collapsed. Jawless fish and placoderms were nearly wiped out, and most trilobites vanished, except for a small group called the Proida. Another extinction event followed close behind at about 359 million years ago, wiping out even more marine life, including calcite sponge reefs and the last of the placoderms. These twin disasters nearly ended the age of fishes and shook the Earth's ecosystems to their core. As for the continents themselves, the Dionian world was shaped by three great landmasses. In the south lay the vast supercontinent, to the north was the smaller continent of Siberia, and in between sat the medium-sized continent called Lucia. Great geological changes were underway. The ancient Ray Ocean was closing. South China was drifting away from Gondwana, and a new ocean, the Paleotis, was opening. Meanwhile, as continents drifted and collided, new mountain ranges began to rise. In North America, this resulted in the Akkadian orogeny, while in Europe, it marked the beginning of the Verascanogeny. These early mountain-building events would eventually lead to the formation of Pangaea, the supercontinent that would dominate the late Paleozoic. The climate during the Dionian was generally warm, though there may have been glaciers at certain times, especially during the early and middle Dionian. Unlike today, the temperature difference between the equator and the poles wasn't very large. The equator was especially dry, with arid conditions stretching across vast regions. By studying microscopic fossils called, scientists estimate that tropical sea temperatures in the early Devonian averaged around 30 or 86 F. The overall mean surface temperature was probably about 16 C or 61 F. One of the most important climate changes in the Devonian was a major drop in carbon dioxide levels. The new forests that had spread across the land were pulling carbon dioxide out of the air and locking it into sediments. This led to a significant cooling event in the middle Dionian, with temperatures falling by as much as 5 C or 9 F. Later on in the late Dionian, temperatures rose again to levels similar to those in the early Devonian. Interestingly, carbon dioxide did not rise with the warming. Instead, increased continental weathering, the breakdown of rocks on land, likely caused the warming. Fossil plant evidence also supports the idea of a hotter, late Dionian climate. These swings in temperature affected the coral reefs to dot in warmer times. Microbes built reefs. In cooler times, corals and sponges dominated. But by the very end of the Devonian, the planet began cooling again sharply. This shift ushered in the late Paleozoic Ice Age, a period when vast ice sheets covered parts of the Earth. During the Dionian period, which began around 419 million years ago and ended about 359 million years ago, sea levels were generally quite high. The oceans of that time were full of life, especially in the shallow waters near the coasts. Many kinds of ancient sea creatures thrived during this era. These included tiny tooth-like creatures called conodonts, colonies of filter-feeding animals known as bryozoans, and brachipods, which looked a bit like modern clams, but were actually quite different. There were also mysterious organisms called hedolids, tiny tube dwellers called microconchoids, and various types of corals that helped form reefs. Graceful, flower-like creatures known as crinoids, which were actually animals related to sea stars, were especially abundant. Although they looked like underwater flowers swaying in the current, trilobites, which had once dominated the seas in earlier times, were still present, but not as widespread as before. Bivalves, ancestors of modern clams and mussels, became common in deeper ocean waters and on the outer parts of the continental shelves. One of the most exciting developments during the early part of the Devonian, around 400 million years ago, was the appearance of the very first ammonites, coiled-shelled creatures related to modern squids and octopuses. Around the same time, bactroids also made their first appearance. Both these groups began to thrive and multiply, possibly because the deep ocean had less oxygen than before, which put stress on older groups and opened up opportunities for new ones to take over. Meanwhile, in the world of fish, big changes were underway. Ancient jawless fish, which were covered in bony armor and called ostracerms, began to fade away. Taking their place were fish with jaws known as enthosts, which were better at hunting and defending themselves. These jawed fish flourished both in the seas and in freshwater rivers and lakes. Among them were placoderms, which were heavily armored and dominated the early Devonian waters. However, they eventually went extinct near the end of the period, possibly because they couldn't compete with other faster and more efficient fish. Also emerging were the early ancestors of modern sharks and rays, known as chondondri, and bony fish called ostracids. These groups became very diverse and played a major role in Devonian marine life. One of the first well-known sharks, called claddoche, appeared during this time. Because of this explosion of fish diversity, scientists and popular writers often refer to the Devonian as the Age of Fishes. At the same time, marine life that could swim freely in the open water, called nekton, began to multiply and diversify thanks to the huge number of tiny planktonic organisms floating in the seas. The ocean floor was already crowded with creatures, so more animals began to live and hunt in open waters. This shift toward a swimming lifestyle is known as the Devonian nekton revolution. However, not all scientists agree this was a true revolution. A study published in the year 2018 argued that, although the percentage of nektonic species rose between the Silurian and Devonian periods, it actually dropped again during parts of the Devonian, especially in the Pian Age. The study suggested that nektonic diversity wasn't especially high in the Devonian compared to other time periods like the Wenlock to Locoin, which came earlier, or the Carboniferous to Permian, which came later. Instead of being a sudden change, they believed this growth in swimming animals was part of a longer, slow trend across the entire Paleozoic era. Back on Earth's surface, one of the most fascinating structures from this time was a huge barrier reef in what is now the Kimberley Basin of northwestern Australia. This reef stretched for about 350 kilometers, which is around 220 meters. Unlike today's coral reefs, which are mostly built by modern corals and algae, Devonian reefs were built in different ways. Some were microbial reefs, made mainly by ancient cyanobacteria that could carry out photosynthesis. Others were coral stromatoporoid reefs built by coral-like creatures called stromatoporoids, along with tabulate and rugose corals. During the warm, early, and late parts of the Devonian, microbial reefs dominated, but during the cooler Middle Devonian, the coral strata reefs were more common. On land, life was changing just as dramatically. By this time, Earth's surface had already been partly green thanks to the mosses and algae that had appeared during the Curon period. But early in the Devonian, more complex land plants began to appear. These new plants had simple roots and created the first real soils. They were joined by tiny land animals like mites, scorpions, myriads such as centipedes and millipedes and trigonautoid, all of which thrived in this new green world. Some of these animals may have lived on land even earlier, possibly as far back as the Cambrian period, based on ancient track fossils like those of Prototinid. One of the most bizarre land organisms at the time was Prototaxides, a giant organism that towered up to 8 meters, around 26 feet tall. It looked like a tree trunk, but wasn't a plant. Some scientists think it might have been a huge fungus, while others believe it could have been a rolled-up mat of liverworts, or something else entirely. Insects may have appeared during this time, too. Fossils from the early Devonian, around 416 million years ago, include possible early insect remains. As for vertebrates moving onto land, there are fossil traces from the Middle Devonian that suggest the presence of early tetrapods, the first four-limbed animals that would eventually give rise to amphibians, reptiles, and mammals. However, some scientists think these traces might actually belong to fish digging for food rather than true landwalkers. Most of the earliest Devonian land plants were small, had no true leaves, and spread by spores or vegetative growth. For example, plants like Dronophycus grew in this way. One of the earliest known plants, Cuconia, was only a few centime tall and had simple branching stems with spore capsules at their tips. A huge milestone occurred during the Middle Devonian when plants with woody tissues appeared. Fossils of a plant called Amaraphyton chatpanins, dated to about 400 million years ago, show the earliest evidence of wood. Soon after, true trees began to grow, including early types of liopods, as well as other tall plants like Cladoxopsids and Archipteris, which belong to a group called Progenosperms. These plants had true leaves and roots, and thanks to a strong material called lignin in their tissues, they could grow tall and resist disease and herbivores. Some of the world's first real forests appeared during the Ilian Age, made up mostly of these cladolopsid trees. By the end of the Devonian, plants that produce seeds had started to evolve. The rapid development and spread of many types of plants during this time is often called the Devonian explosion or the Silurian-Devonian terrestrial revolution. All this plant growth had another powerful effect. It pulled carbon dioxide out of the atmosphere. This helped to cool the global climate, but it may have also contributed to a major extinction event as the environment began to change too quickly for many species to survive. As plants with stems, leaves, and roots became more complex and began to cover the land in the late Devonian period, a group of ancient creatures known as aeropods evolved right alongside them. These animals, which include early ancestors of insects, spiders, and crustaceans, gradually adapted to life on land, finding shelter, food, and a place to thrive in this new world of growing forests and rich vegetation. During this time, something remarkable began. Insects and seed-producing plants started forming close relationships. This early partnership between bugs and plants would eventually shape the modern ecosystems we know today, where bees pollinate flowers and plants depend on animals to spread their seeds. It all began in the late Devonian, a time when land life was just beginning to find its rhythm. As plant life spread and roots dug deep into the earth, soils began to form, and this caused big changes to how wind and water shaped the land. Erosion and the way sediment was deposited in rivers and oceans shifted, with the land becoming more stable and full of plants and crawling creatures. Vertebrates, the first animals with backbones, began to test life on land. By the end of the Devonian period, arthropods had already become fully established in terrestrial environments. But even as life was thriving on land and in the sea, the Earth was heading into one of the greatest extinction crises in its history. The late Devonian extinction wasn't just one event. Instead, it was a series of powerful extinction pulses that struck over millions of years. These occurred at three key times: at the boundary between the Gavetian and Frasnian stages, then between the Frasian and Finian stages, and finally near the transition from the Devonian to the Carboniferous period. Altogether, these extinction events are considered one of the Big Five mass extinctions in Earth's long history. The crisis mainly hit life in the oceans, especially creatures that lived in warm, shallow waters. Cool water species were less affected. One of the hardest hit groups were the reef builders, which had created the enormous and beautiful reef systems of the Devonian seas. These ancient reefs, some of the largest the world has ever seen, vanished almost completely. Many other sea creatures suffered terribly as well. Brachiopods, trilobites, ammonites, and acrits were all seriously reduced in number. Conidans and bony fishes, two major groups of early vertebrates, lost about 96% of their species. Even more devastatingly, all the ostracoderms, jawless, armored fish, and plecoderms, heavily armored oarfish, disappeared entirely from the world's oceans. Surprisingly, life on land was not hit as hard. Plants and freshwater creatures, including the ancient four-legged ancestors of amphibians and reptiles, known as tetrapods, survived the crisis. However, some scientists argue that early tetrapods may have come close to extinction as well, though evidence is still debated. The true cause of the late Devonian extinction remains one of science's unsolved mysteries. Many theories have been proposed, but none are confirmed. One idea suggested by Canadian paleontologist Digby McLaren in the year 1969 is that the extinctions were caused by the impact of an asteroid. While there is evidence of asteroid collisions during the late Devonian, such as the Alamo impact, there is no solid proof of a large enough crater from that time to explain such widespread devastation. Music, the Carboniferous period, was a major chapter in Earth's long history. It was part of the Paleozoic era and lasted for about 60 million years. Beginning around 358.6 million years ago, at the end of the Devonian period, and ending roughly 298.9 million years ago, marking the beginning of the Permian period. This period was the fifth of 6 major divisions within the Paleozoic era, and also the fifth period in the broader timeline known as the Phaneroic Eon in North America. Geologists often split the Carboniferous into 2 smaller time blocks, the Mississippian earlier and the Pennian later. During the Carboniferous, life on land had become well established. Animals with backbones that had 4 limbs, known as tetrapods, were thriving. These creatures had evolved from lobofinned fish during the Devonian, and by the Carboniferous had developed 5 fingers or toes on each limb, a trait known as being pentadactylous. Because amphibians were so common and widespread during this time, the Carboniferous is often nicknamed the Age of Amphibians. One large group of amphibians, called tenospondylus, became the dominant animals on land. Even more significant was the first appearance of amnia, a new group of land animals that laid eggs on land. This group split into 2 major branches: synapsids, which would eventually give rise to mammals, and sauropsids, the ancestors of today's reptiles and birds. At the same time, land-dwelling aeropods, such as arachnids, like giant scorpions, and spider-like creatures, myriads, such as the massive millipede like Europa, and especially insects, including the first flying ones, went through an explosion of new forms and diversity. Towering forests filled with giant ferns, seed ferns, and club mosses covered the land, growing in huge, swampy environments. Over millions of years, the remains of these dense forests were buried and turned into thick layers of coal, which is why this period is called the Carboniferous, a name that means coal-bearing. In the later part of the Carboniferous, the Earth went through a period of cooling, and glaciers formed in parts of the southern hemisphere. Sea levels dropped, and the continents slowly drifted together to form a massive supercontinent called Pangaea. Near the end of the period, a minor extinction event occurred, known as the Carboniferous rainforest collapse. This event, driven by changing climate, caused many rainforests to disappear, and led to the extinction of several species. For a long time, scientists believed that the level of oxygen in the atmosphere during the Carboniferous was always very high, much higher than today. But more recent studies suggest that oxygen levels actually varied over time. They started out low, but then rose sharply, at times reaching as high as 25 to 30% compared to about 21% today. This high oxygen content may have allowed some insects and aeropods to grow to enormous sizes. The idea of organizing Earth's layers of rock into a time system began in the late 18th century. The name Carboniferous was first used in 1799 by the Irish geologist Richard Cherwin. Later, in 1811, it appeared in print as part of a heading by John Ferry Sr., Coal Measures, or Carboniferous Strata. 4 main rock layers were originally included: Old Red Sandstone, Carboniferous Limestone, Millstone Grit, and the Coal Measures. In 1822, then in 1835, Phillips named it the Carboniferous System. Eventually, scientists realized that the Old Red Sandstone actually belonged to the older Devonian period, because rock layers in the British Isles were very similar to those in Western Europe. Scientists created a shared European system. The Carboniferous was divided into 2 major parts: the lower Donantian dominated by limestones, and the upper Scission, which was mostly sandstone and shale. The Dimension was further split into the Tornian and Visan stages. The Silesian was divided into the Nemorin, Westphalian, and stages. In North America, geologists observed a similar pattern, but chose to split the Carboniferous into two separate systems: the Mississippian, rich in limestones, and the Penian, rich in coal and shale. These two divisions were officially recognized in 1953 by the United States Geological Survey. In Russia, geologists in the 1840s divided the Carboniferous into lower, middle, and upper sections, using rock layers from Russia. By the 1890s, these divisions were named Dancian, Moscovian. The Sepovian stage was added to the lower Carboniferous, while the Moscovian and Gillian made up the upper part. Later, the Bashirian stage was added in 1934. In 1975, the International Commission on Stratigraphy, ICS, officially standardized the Carboniferous timescale. They kept the Mississippian and Penian from North America, the Tunisian and Visayan from Western Europe, and the Sarpovian, Bashkirian, Moscovian, and Gillian from Russian geology. This made earlier terms like Dimension and Silian mostly outdated, though some are still used in Europe today, to help geologists across the world agree on time periods. The ICS uses a method called the Global Boundary Straightweight Section and Point GSSP. This means picking a specific rock layer at a specific location to mark the beginning of a stage. So far, the Carboniferous system and only 3 of its stages have officially defined GSSP boundaries because the rocks and fossils can be complicated and hard to match globally. The name Mississippian was first proposed by Alexander Winchell in 1870, based on rock layers seen along the upper Mississippi River. During this time, a shallow sea connected the Paleotized Ocean with the vast Panthalassic Ocean, allowing sea creatures to spread around the world. This made it easier to match rock layers using fossils. However, there are very few volcanic rocks from the Mississippian, so dating those rocks precisely is difficult. The Tournasian stage, named after the city of Tura in Belgium, was introduced by André Dumour in 1832. The GSSP, marking the start of this stage and of the entire Carboniferous period, is found in southern France at a place called LA. Scientists initially define the boundary based on the appearance of a fossil called Siphonodella, but later studies showed problems with this method, making it hard to line up the exact timing worldwide. The Visan stage, also named by Dumont in 1832, is named after the town of Visay in Belgium. Its GSSP is now placed in southern China based on the appearance of a type of fossil called Eoperistella simplex, a kind of tiny shelled creature. This decision was made in 2009. The Serpovian stage was first proposed in 1890 by Serge Nikitin and named after the city of Sarakov near Moscow. It still does not have an officially chosen GSSP. The boundary between the Visan and Serpovian stages coincides with a time of major climate cooling and the spread of glaciers. This caused sea levels to drop and isolated many marine habitats, which made species evolve differently in different places, making it harder for scientists to match layers globally. Researchers are still working in places like the Urals and southern China to find the best spot for defining this boundary, possibly using the first appearance of a fossil named Loria ziegler. The Penian period gets its name from the U.S. state of Pennsylvania, where thick layers of coleric rock are widely found. This name was first suggested by the geologist J.J. Stevenson way back in the year 1888. During the Permian, some major changes were happening on Earth. One of the biggest was the closing of the Reich Ocean and the slow joining of the Earth's land masses to form the supercontinent Pangaea. At the same time, large parts of the southern continent Gondwana were covered in thick ice sheets. This combination of continental movement and glaciation caused major shifts in climate and sea levels. These changes affected where marine animals could live, making them more localized. As a result, it became harder for scientists to compare rock layers, called biorotographic correlations, across different parts of the world. Luckily, the process of Pangaea's assembly also triggered many volcanic eruptions. These volcanic layers can be dated more accurately using radiatric dating, making the Pennsylvania easier to study than the earlier Mississippian period. Bashkarian stage is the first stage of the Permian period. It was proposed in the year 1934 by a Russian geologist named Sofia Simikatova. She named it after Bashkira, the older name for the region now known as the Republic of Bashkortostan, located in the southern Ural Mountains of Russia. The official start of the Permian and the Bashkiran is marked by the appearance of a tiny fossil called the conodont, Declinignathus nodularis. This boundary is recorded at a place called Arrow Canyon in Nevada, United States, and was officially recognized in the year 1996. Back then, Arrow Canyon was part of a warm, shallow tropical sea stretching all the way from Southern California to Alaska. The rock layers there show a repeating pattern called a cyclone, made of alternating shallow marine limestones and sandstones, followed by mudstones and broken up limestones, showing the rise and fall of ancient sea levels. The Moscowian stage is named after marine limestones and colorful clays found near Moscow, Russia. This stage was introduced in the year 1890 by geologist Sergei Nikitin. Unfortunately, this stage still doesn't have an officially defined starting point or GSSP, Global Boundaries Strait Oip section and point. In northern and eastern parts of Pangaea, a tiny single-celled fossil called Algetoella algetovica could be used to mark the beginning of this stage. However, because it's only found in limited regions, it's not helpful for worldwide comparisons. Other possible boundary markers include the appearance of conodonts like Declinus denisis or Edonthoids poscatus sites in the Ural Mountains and in Nui in Gudro Province. Southwestern China are being considered as candidates for defining this boundary. The Casimovian is the first stage of the Upper Permian. It was named after the city of Kasimov in Russia and was originally part of Nikitin's Moscowian stage. Later in the year 1926, A.P. Ivanov recognized it as a separate unit and gave it the name Tigalathena horizon, based on a kind of fossilized brachipod. The beginning of the Casimovian occurred during a time when global sea levels were unusually low, which left gaps in rock layers from that time. This makes it hard to find fossil species that are useful for worldwide correlations. Like the Moscowian, the Casimovian still does not have an officially chosen GSSP. Possible sites include the southern Ural Mountains, the southwestern United States, and the Shuar in China. The Gilian is the final stage of the Permian. It's named after the village of Gel near Ramenskoye in the Moscow region. Once again, Sergei Nikitin defined it back in the year 1890. This stage also lacks a GSSP. Fossils of fuselinids such as Rauserites, Rozicus, and Stukenberg are useful for dating rocks in areas like the Boreal Sea and the Paleocean region, but they are not found in eastern Panja or the edges of the vast Panthalassa Ocean. Scientists are considering sites in the Urals and Gu China to define this stage more precisely. The transition from the Penian to the Permian period is marked by a GSSP located in the Adirlish River Valley near the city of Aktob, Kazakhstan. This boundary, officially agreed upon in 1996, is marked by the first appearance of a fossil conodont named Streptonathus postphus. A cyclone is a repeating pattern of rock layers made up of both marine formed under the sea and non-marine formed on land sediments. Each cyclothem reflects a single sedimentary cycle, beginning with an erosional surface at its base, though each one may only be a few meters thick. When stacked together, they can form sequences that are hundreds or even thousands of meters thick. Cyclones formed along continental shelves, which were extremely shallow and flat. This meant that even a small change in sea level could shift the shoreline dramatically, either flooding the land or exposing large areas to erosion. The main era of cyclone formation was during the late Paleozoic Ice Age, which lasted from the late Mississippian to the early Permian periods. As glaciers grew, they pulled water out of the oceans, causing sea levels to drop. Rivers then carved channels into the exposed land, and plant roots broke down rocks to form soils. These layers of non-marine sediments formed the base of each clone. When glaciers melted, sea levels rose rapidly. Wet lowlands turned into pea swamps, and thick layers of plant matter built up in these oxygen-poor environments. Over time, this plant material turned into coal. As the seas advanced, they flooded these peatlands, depositing delta, lagoon, and estuary sediments. Eventually, fully marine conditions returned, covering everything with layers of limestone, followed by deep-water black shales as sea levels reached their peak. Although sea levels fell again later, the process was slower and often eroded previous layers rather than building new ones. Because the rise in sea level was so fast, the resulting sediment layers were usually less than 10 meters thick. During the Penian, cyclotherms were common in shallow tropical seas that covered areas of a region that included what is now the western and central United States, Europe, Russia, and Central Asia, as well as parts of the North and South China. These repetitive sea level changes mirrored the glacial cycles of the late Paleozoic Ice Age. Each cycle followed a pattern known as a 100,000-year Milankovitch cycle, the same rhythm that controlled the advance and retreat of the glaciers on Gondwana. Coal, the dark, energy-rich rock we use for fuel, was formed from layers of dead plant material that built up in soggy oxygen-poor swamps called peat mires. In these waterlogged places, decaying plants piled up without fully rotting. Over millions of years, this thick, spongy layer of peat was buried under heavy sediments. The pressure and heat from the layers above slowly turned it into coal. Most of the world's coal was created during a very special time in Earth's history, between the late Carboniferous period and the early Permian period. That means most coal on Earth was formed roughly between 323 million and 285 million years ago. The plants that filled these ancient swamps didn't just become coal. They also helped change the chemistry of Earth's air, especially by increasing the amount of oxygen. During the part of the Carboniferous period known as the Permian, huge amounts of plant material collected in vast, swampy wetlands located near the equator. These lush, low-lying regions stretched across what are now the remnants of the central Pangaean Mountains in an ancient landmass called Lucia, as well as around the edges of what we now call the North China and South China. During colder times, known as glacial periods, sea levels dropped, revealing wide areas of land that had previously been underwater. Enormous rivers, some several km wide, carved through these newly exposed lands, feeding into networks of smaller rivers, lakes, and swampy peat meres. When the earth warmed again and the glaciers melted, sea levels rose, burying these wetlands under mud and sand. This cycle of exposure and burial happened again and again for millions of years. Over time, the weight of new sediments pressed down on the buried peat, turning it into thick layers of coal. In other parts of the world, such as Siberia and Western Australia, smaller coal swamps also formed, especially during warmer periods, filled with plants that could survive in more temperate climates. Scientists still debate why Earth saw this dramatic surge in coal formation, specifically during the Carboniferous period. One popular idea, known as the delayed fungal evolution hypothesis, suggests that trees evolved to produce a tough material in their wood called lignin, which resists decay. However, fungi that could break down lignin hadn't evolved yet. So for a while, dead trees and plants simply piled up, creating vast quantities of undead organic material. Genetic studies of certain fungi, called Basidia, the group that includes mushrooms, suggests they didn't develop the enzymes needed to digest lignin until the Permian period, which came later. But this idea is still debated. Some evidence shows that even by the end of the Devonian period, fungi might have already begun breaking down lignin, even if they weren't yet using the exact enzymes that modern fungi use. Another theory points to Earth's unique geography and climate during the Carboniferous. At that time, many continents were clustered near the equator, where the climate was hot and humid. The land was flat, low-lying, and slowly sinking, perfect conditions for forming endless swamps. This setting, along with very high levels of plant growth and productivity, could explain the massive buildup of peat and the surge in coal formation. This entire period happened during a long stretch of Earth's history known as the Late Paleozoic Ice Age, often abbreviated as LPIA, was the longest and most intense ice age of the last 540 million years, beginning in the late Devonian period around 365 million years ago and ending in the Permian about 253 million years ago. Temperatures began to fall toward the end of the Devonian. A brief glacial episode happened during the Phoenician Age, just before the boundary with the Carboniferous. This was followed by a short, warm period known as the early Tornian warm interval. After that, more carbon was buried as organic matter, and oceans became low in oxygen, causing the climate to cool even more. This triggered glaciation in Earth's southern polar regions. During a later warm phase called the Vician warm interval, glaciers retreated far back, surviving only in high mountain regions such as the Protos of Bolivia and Argentina and the ancient Pan-African mountains of Brazil and Africa. The main phase of the late Paleozoic Ice Age started around 335 million years ago and lasted until about 290 million years ago, as temperatures dropped and carbon dioxide levels in the atmosphere fell. Sea levels dropped around the world, and enormous glaciers began forming. These icy centers, up to 30 in number, spread across the ancient supercontinent Gondwana, reaching into parts of what are now Eastern Australia, northwestern Argentina, southern Brazil, and southern Africa. Scientists believe this dramatic drop in carbon dioxide was caused by the rise of the Central Pangaean Mountains. As these mountains formed and eroded, rocks were weathered, pulling carbon dioxide from the air. The closing of a seaway between the Ryak Ocean and the Tethys Ocean may have also helped cool the climate by changing oceans, currents, and how heat moved around the globe. Despite the Ice Age, there were still periods of warming. Warmer intervals occurred during the Bashiran, the late Moscowian, and from the late Casimovian to the Middle Geon, when ice melted, glacial debris disappeared, and sea levels rose once again. During the early Casimovian age, about 305 million years ago, Earth experienced a sudden, intense glaciation lasting less than 1 million years. During this brief cold spell, atmospheric carbon dioxide levels dropped to just 180 parts per million, lower than today's levels. But this cold snap ended just as suddenly when CO2 levels shot up to around 600 parts per million, warming the planet. This spike may have been caused by large volcanic eruptions or a slowdown in the burial of organic matter. The coldest part of the late Paleozoic Ice Age came around the boundary between the Carboniferous and Permian periods. Evidence of glaciers from this time has been found across South America, Africa, Antarctica, Australia, Tasmania, India, the Arabian Peninsula, and blocks of land known as the Samnian terranes, showing that huge ice sheets once spread across the southern half of Earth. At the same time, carbon dioxide levels dipped again down to around 175 parts per million and stayed below 400 parts per million for the next 10 million years, largely because erosion of volcanic rock absorbed CO2 from the air to figure out what the atmosphere was like back then. Scientists use several different techniques. Some, like trapped gas bubbles in ancient salt crystals, howlite, give snapshots in time. Others, like charcoal from ancient wildfires or the presence of certain minerals, like pyite, give broader trends. Charcoal became more common in the fossil record, starting in the late Devonian, which suggests that atmospheric oxygen levels were rising. Many scientists think oxygen levels were above 21% for most of the Carboniferous. Gas bubbles trapped in helicate crystals from 337 to 335 million years ago suggest oxygen might have been around 15% during the Wisent. Though this comes with a lot of uncertainty, pyite records show that oxygen started around 15% in the early Carboniferous, climbed above 25% during the Permian, and then fell below 20% by the end. Though the exact numbers vary, all studies agree that oxygen levels in the Carboniferous rose from around 15 to 20% at the beginning of the period to peaks of 25 to 30% later on. these changes weren't steady. They rose and fell, depending on the shift in climate. Some researchers believe these high oxygen levels helped support the giant insects and other large creatures that lived during the Carboniferous. But this idea is still being explored and debated today. As the Earth's climate shifted during the Carboniferous period, these changes were reflected in how sediments were deposited across different regions. In the early part of this time, specifically during the early to middle Mississippian, which spanned roughly from 359 million to around 323 million years ago, the oceans were relatively warm. In these warm, shallow seas, large amounts of carbonate materials, such as limestone, were produced. These carbonates spread far and wide, covering the gentle continental slopes of what are now known as Lucia, a landmass that included parts of North America and Europe, as well as the ancient continents of North and South China. The geological setup during this time resembled what scientists call a carbonate ramp, a gently sloping underwater landscape where sediment slowly built up layer by layer around the coastlines of Laurussia, Kazakhstania, and northern Gondwana. Thick beds of evaporate minerals such as rock salt and gypsum were also forming due to the evaporation of shallow seas. But as time passed and the climate cooled, starting in the late Visayan Age, which occurred around 330 million years ago, these carbonate-producing processes became limited. They could no longer happen in deep waters and were now restricted to shallower depths, usually less than 10 meters. This led to the development of broad, flat carbonate platforms, with steep edges similar to the kind of underwater cliffs found in today's marine environments. By the time of the Moscowian Age, which began around 315 million years ago, Earth's ice sheets were expanding and shrinking in cycles. These glacial cycles led to the formation of special types of sediment layers known as cyclones. These cyclones were made of alternating beds of carbonate and silic sediments, materials like sand and silt, and were deposited across continental shelves and platforms as sea levels repeatedly rose and fell. As glaciers grew and then melted with the seasons, icy waters flowed along the edges of the Gondwan and continent, bringing nearly freezing temperatures to the surrounding seas. Evidence of this can still be seen today in the presence of glendonite, an unusual mineral that forms from equity, a type of calcium carbonate that only crystallizes in cold water. These glendonites are found in fine-grained marine sediments, indicating the chilly conditions at the time. The movement of glaciers across Gondwana and the rising central Pangaean mountains ground up rocks and produced vast amounts of fine silt-like sediment. Winds carried these tiny particles across the equator, creating widespread blankets of low, dusty, fertile soil that once covered large areas of what would become central Pangaea. This period of intense glaciation, known as the Late Paleozoic Ice Age, or LPIA, was initially seen as a crisis for marine life. Many species disappeared, and for a time, overall biodiversity was low. But newer research shows that this wasn't just a time of loss. The sudden and extreme shifts in climate and environment actually encouraged rapid evolution and the appearance of many new marine species, a phenomenon scientists call an adaptive radiation. The constantly changing climate also reshaped the vast tropical forest of Laurasia many times. Sometimes they were swampy wetlands, and at other times they became dry seasonal forests. During the glacial episode known as the Casimovian, which began around 307 million years ago, many of the towering tree-like lapids and other wetland plants declined or disappeared. This drop in biodiversity is closely linked to a sharp fall in atmospheric carbon dioxide levels, which fell below 400 parts per million. While some have called this event the Carboniferous rainforest collapse, it was not the complete end of rainforests. Instead, one type of rainforest ecosystem was gradually replaced by another. As the Carboniferous period gave way to the Permian around 299 million years ago, conditions became even drier. Especially in low-latitude regions, the carbon dioxide levels dropped further, and new types of forests took over. These forests were adapted to survive in seasonally dry environments. Around this time, four-legged animals known as tetrapods also developed new features that helped them live on land, and many new dryland-adapted reptiles known as amniote began to thrive and spread. The land plants of the early Carboniferous period, some of which have been preserved in lumps of coal known as coal balls, were quite similar to those from the late Devonian period before them. But new plant groups also emerged. Among the main plant groups of the time were the equiseidals, giant relatives of modern horsetail, sphenophiles, climbing plants, liquodials, club mosses, lepidendrales, scale trees, felicicles, ferns, medullacales, often called seed ferns, and cordials, an early group related to conifers. These plants continue to dominate the Carboniferous landscape. In the later part of the period, more plant groups appeared, including the Psychodophyta psychocads, calistophytales, another group of seed ferns, and the vaults, early conifers. Some lichwites from the Carboniferous, especially those in the leopard dendrials group, were nothing like the small club mosses we see today. These were giant trees, some reaching heights of 30 meters, and with trunks up to 1.5 meters wide. They included plants like Lepida, Dendron, Anabathra, Lepida floros, and Sigillaria. Their roots, known by the fossil name Stigmaria, formed thick underground networks. Unlike modern trees, their strength came from a thick outer tissue called the cortex rather than the inner. Another ancient group, the Cladoxopsids, were towering plants that eventually gave rise to true ferns. Many fern fronds from the Carboniferous period look so similar to living ferns today that it's hard to tell them apart. Some of these ancient ferns may have even lived on other trees as epiphytes fossil. Records include many types of ferns and seed ferns like Pica, Neuropteras, Allothopteras, and Sphenopteras, as well as tree ferns such as Megapion. The equity also included the massive calamites, which had hollow-jointed stems that could reach up to 20 meters in height and 30 to 60 centimeters in thickness. Another climbing plant, Phenopilm, had wefts of narrow leaves and was probably related to both calamites and liopods. The tall and strapped cordytes grew between 6 and over 30 meters high and are thought to be early relatives of cycads and conifers. They bore seed-like structures called cardiorpus and likely thrived in swampy environments. True conifers, like Valia, part of the vaults order, arrived later in the Carboniferous and preferred drier upland areas. Underwater life was also flourishing. Marine invertebrates were diverse and included foraminifera, corals, bryozoans, ostracods, brachiopods, ammonoids, heteroloids, microconids, and crinoids. Brachiopods and fusulinod Foraminifera became especially abundant from the Vishon onward, although some groups, like cephalopods and conidans, began to decline. This boom in marine life diversity is known as the Carboniferous earliest Permian biodiversification event. One of the most common and successful phenomena of the time was the genus Fusulina, which lived in ancient seas across present-day Russia, China, Japan, and North America. Microscopic shelled creatures like radularians have been found in rocks called church from regions such as Devon and Cornwall in England, and across Russia and Germany. Sponges too were common, including various groups like Catulluscus, Gerticoia. Coral reefs continued to grow, filled with diverse species such as Canenia, Neophrentis, and Miscellania. The fan-like phenestellid biozones were particularly abundant, including the screw-shaped Archimedes and genera like Phenestella and Polypora. Brachiopods also thrived, some growing as large as 30 centimeters wide, like the giant Gigantus, while others, like chonids, were smaller and simpler in shape. Other groups, such as atheridids, spirids, rhynchonellids, and terebralids, were common too. Some inarticulate brachiopods, like Dina and Crania, also lived widely. Worm-like annelids, such as serpolites, appear in many fossil layers, while mollusks continue to grow in number and variety. Bivalves like avicular pecten, Posidonomia, and Carbonicola were common, as were gastropods like Merconia, Euompulus, and Natocopsis. Nautiloid cephalopods became rarer, but tightly coiled nautilids and gonatite ammonoids like Enigmatisrus were still widespread. Trilobites, once abundant, had become rare and were now represented only by a group called proadids. Tiny ostracods, a type of crustacean, were still common with many genera, including Baria, Corallina, and Hollanella. Crinoids, often called sea lilies, were especially numerous. Some formed dense underwater meadows, and when they died, their remains created thick layers of limestone. Common genera included Cathecrinus, Woodocrinus, and Actinid. Sea urchins, like Archaeoidus and Palochinus, also lived during this time. Blastoids, which resembled crinoids and had long stalks that anchored them to the seafloor, reached their peak in this period. These included families like Pentranetidae and Cauteridae, showing just how rich and strange the underwater world of the Carboniferous truly was. During the Carboniferous period, an age that spanned tens of millions of years, life both in water and on land was incredibly rich and diverse. Freshwater habitats were teeming with invertebrates. Some of the most common freshwater and slightly salty water animals were bivalve mollusks like Anthronia, Naiadites, and Carbonicola, which had hard shells and lived in rivers and swamps. There were also many different crustaceans, creatures with hard outer shells and jointed legs, including species like Candona, Carbonita, Darwinola, Etheria, Anthocharis, Ditherocharis, and Another fascinating group were the Europarids, also known as sea scorpions. These were among the largest arthropods to ever live. Some Carboniferous creatures were unlike anything alive today. Adolophthalmus megarock, once thought to be a giant spider, lived in shallow waters. Another, the massive Hibbertopterus, may have ventured onto land for short periods. These creatures were likely amphibious, moving between water and swampy ground. From time to time, the seas returned to these low-lying swamps. When they receded, they left behind thin layers of sediment called marine bands. These bands preserved fossils of marine life, including Lingula, Orbiculoidea, and Productus creatures that thrived in brackish or salty waters. Life on land was equally dramatic. Air-breathing arthropods spread widely. Fossils show early insects, centipede-like myriapods, and spiders from the arachnid family. Some arthropods grew to enormous sizes. The largest was Arthroplura, a millipede-like giant stretching up to 2.5 meters or 8.5 feet. It remains the biggest land-dwelling invertebrate. Early in the Carboniferous, the first winged insects appeared. Soon the skies were filled with giants. The Protodona, also called griffinflies, were among the most impressive. One, named Meganeura, resembled a dragonfly but with a wingspan of 75 centimeters or 30 inches, the largest flying insect ever known. Other insect groups also thrived. Chaetynopterygata, early relatives of mayflies. The plant juice feeding Polyadixioptans, often large and abundant. Plant-eating Protothopterans, and the Dictyoptera, primitive ancestors of cockroaches. These insects filled the Carboniferous skies, forests, and swamps. Many of these fossils were uncovered in rich coal beds, the fields of Saarbrücken in Germany, Commentry in France, and even inside the hollow fossilized tree trunks of Nova Scotia. Canada revealed this ancient insect world. British coalfields gave us beautifully preserved fossils. One example is Archopoptilus, an insect with wings over 4 centimeters wide, about 2 inches. Some fossils, like those of the genus Brodia, still show traces of bright colors on their wings in Nova Scotia. Inside ancient hollow tree trunks, scientists discovered early land snails. These included archizonids and Dendropupa, some of the earliest shelled creatures to live on land. The seas of the Carboniferous were rich with fish. Among them were the elasmobranchs, the group that includes sharks and rays. Some, like Psammodus, had flat, crushing teeth for breaking shells of brachiopods and crustaceans. Others, like the Tenacanthiforms, grew to massive sizes. Fossils suggest that species such as Pseudus may have reached 6 to 9 meters, or 20 to 30 feet long. Sharp-toothed hunters also lived in these seas. The Simarita and Petalodons had unusual circular slicing teeth. Most of the large cartilaginous fish lived in salt water, but some, like the xenocants, adapted to the freshwater swamps of the coal forests. Others, like Bandringa, swam far inland into rivers. Bony fish also thrived. A group called Polianiciforms lived near the coasts. The Sarcopterygians, or lobe-finned fish, included giants like rhizopus. These massive predators may have ruled the waterways. Most of what we know about Carboniferous fish comes from their remains. Fossilized teeth, spines, and bits of armored skin are the most common finds, but small freshwater fish are sometimes preserved whole. These include species like Caetenatus, Urinamus, Acanthidus, Gyroptychus, and Gyrocanthus. During this time, cartilaginous fish as a whole went through a burst of evolution. The class Chondrichthyes became more diverse than ever. A subgroup called the Holocephalans, distant relatives of modern-day chimeras, began their rise. You've just traveled through the ancient past of our planet. From oceans filled with strange creatures to glaciers that reshaped the world, the story of Earth is always one of change. Each rise and fall, each extinction and renewal, carried life forward toward the future we know today. As you drift into rest, remember that the ground beneath you, the seas around you, and the sky above you all carry the memory of these deep ages. The Earth is not just our home. It is a living record of time, written in stone, water, and air. Thank you for joining us here on Earth, Analyst. If you enjoyed this journey, be sure to like, subscribe, and return for more stories of our planet. For now, let your mind settle into stillness and let the echoes of Earth's ancient past guide you into peaceful sleep.